When talking about charge and static electricity, we use the unit coulomb, but a coulomb is actually really big. And so we'll usually work with very small amounts of charge in terms of coulombs. And these amounts of charge we're working with are so small that you need to know 3 new metric prefixes to deal with the fact they're so small. The metric prefixes you need to know are first micro, and micro is times 10 to the negative 6. Millimeter is a meter times 10 to the negative third. You move 3 places to the right to convert from meter to milli. To convert from meter to micrometer, you'd move 6 places to the right, just to give you an example of what that means. There's also a nano, which means times 10 to the negative 9th, so down 9 decimal places. And then there's pico, which is times 10 to the negative 12th. You should take a second and memorize this. Nano is very easy for me to remember because nano and 9 both begin with an N, so I can associate those. Micros times 10 to the negative 6, you just have to remember that, and picos times 10 to the negative 12th. You need to memorize these prefixes right now. So actually, why don't you pause the video and just take a second to memorize those. Okay. Also, the prefixes for nano and pico make sense, N and P, but for micro we use a mu, which is drawn like this. So imagine making a U, but one side has a longer kind of stick on the side. So micro, mu, nano N, and pico P. Microcoulombs, nanocoulombs, and picocoulombs. Some information you need to know. The charge on an electron is 1.602 times 10 to the negative 19th coulombs, which we've talked about before. And on an electron, that should be negative. Negative 1.602 times 10 to the negative 19th coulombs. The mass of an electron is 9.11 times 10 to the negative 31st kilograms. The charge on a proton is the positive version of an electron, so positive 1.602 times 10 to the negative 19th coulombs. And the mass of a proton, bigger than an electron, the mass of a proton is 1.67 times 10 to the negative 27th kilograms. Now notice we're dealing with very small numbers, negative 31, 10 to the negative 31st, that's moving the decimal 31 places to the left. 10 to the negative 27th, moving the decimal 27 places to the left, very small numbers. And you might be thinking, whoa, those seem like a lot to memorize. You don't have to. On the AP exam, those 4 numbers will be given to you in what's called a table of helpful constants. So you will have those on the AP exam, but you need to have them written down in your notes to use tomorrow, just so you can refer to them quickly. So if you need to, pause the video and write those down. Let's look at a quick example of how we can use this information. John Travoltage, the guy pictured at right, is neutrally charged and he rubs his feet on the carpet. He acquires a net charge of negative 3.2 nanocoulombs. How many electrons has he gained or lost? All right, so negative 3.2 nanocoulombs is negative 3.2 times 10 to the negative 9th, that should be a 9, negative 9th coulombs. The movement of electrons is what gives him his charge, so we need to figure out how many electrons does it take to get that much charge. So why don't we just divide the charge on one electron and figure out how many electrons that took. So he has negative 3.2 times 10 to the negative 9th coulombs of charge on him. We'll divide that by the charge of an electron, negative 1.60, we can round, times 10 to the negative 19th coulombs. All right, well, this looks like it's going to be fairly simple to me. 3.2 divided by 1.6 is 2. And then we can, since our exponents are divided, we should subtract them, but a negative minus a negative, negative 9 minus negative 19 is the same as negative 9 plus 19. So we get 2.0 times 10 to the 10th electrons. And now if I grab a calculator and confirm that, I get the same answer, 2 times 10 to the 10th electrons. Now I want to know, has his mass changed, and if so, by how much? Well, he gained this many electrons, and on the last slide, I told you what the mass of an electron is. So now I just multiply that many electrons by the mass, and I get how much his mass has changed. So 2.0 times 10 to the 10th electrons times the mass of one electron, which is 9.11 times 10 to the negative 31st kilograms. Well, 2 times 9.11 would be 18.22. This is multiplying, so I add the exponents, times 10 to the negative 21. 10 plus negative 31 is to the negative 21st. So he didn't gain much mass, but he gained some mass. And if he gained those electrons, because he acquired a negative charge, to get a negative charge you have to add in electrons. So if he gained those electrons, his mass went up 18.22 times 10 to the negative 21st kilograms. And I just gave you the argument for how do you know he gained electrons and did not lose protons. One, protons can't move. They're stuck in the nucleus of the atom. So if you think about the picture of the atom, those protons are in the nucleus and they're not going to leave. It requires a nuclear reaction, like an atomic bomb going off, for a proton to get out of a nucleus. Or it requires certain kinds of radioactive decay where atoms shoot out protons. But in average everyday life, electrons are what are moving. So the electron out there in the orbital, not stuck in the nucleus, can move. So if you get a negative charge, you gain electrons. If you get a positive charge, you lose electrons. Any object with mass causes gravity. And the way we express this in physics is with fields. So any object with mass creates a gravitational field. And for gravity, all field lines will point toward the masses. What field lines do is they tell you the way that an object with mass would have force applied on it. So if I stick a mass right here, that field line tells me it will go in. And this other field line's messed up. It should also be pointing in. So if I put an object with mass in a gravitational field, it will move in the direction of the field lines. Field lines are something that we use to show which way forces are applied to objects. And for gravitational fields, we have this equation, weight equals mass times gravity. Now this is where it's going to become important that I told you the units for gravity on Earth are newtons per kilogram. Because in a gravitational field, the unit for a gravitational field are newtons per coulomb. It takes a coulomb to cause a force, just like it takes a kilogram to cause a force. When we draw electric fields, also messed up again there, when we draw electric fields, the field lines point in the way a positive charge would move. Take a second to think about that. These lines point in the way a positive charge would move. So electric field points how a positive charge would move. That means for an electron, the field should point in toward the electron because opposites attract, and so a positive would want to move toward the electron. Any positive particle in the presence of an electron will experience a force wanting to move it toward that electron. Any negative charge in the presence of an electron would experience a force moving it away from the electron. And we can calculate that force by saying the charge on the particle times the electric field created by the electron. So this E is the electric field created by the electron right here. This Q is the charge on the positive particle that we've put right here. So charge on the particle is Q, E is the strength of the electric field. You need to know that equation. Make sure you've got it. Just to review, these are key points. The electric field units are newtons per coulomb, just like gravitational field is newtons per kilogram. The direction of the force is always along the field lines, and we consider those field lines to represent the way a positive charge would move. So if I have a negative charge, like an electron, and then I put a proton next to it, the force will point toward the electron. If I have a negative charge and I put an electron next to it, the force will point away from the negative charge because opposites attract and like charges repel. So the direction of the force is the way that the test particle you put in wants to move. Let's talk about this with this example. I'm going to have an electric field with these lines. And then I'm going to put into the field what's called a test charge. So the only way you can know which way an electric field points is to put a test charge in it. You put a charge in there to test it. So we're going to say we know already that field lines are pointing in the way shown, and we put a positive test charge right here. The question says, what is the magnitude and direction of the force on the proton? Well, to get the force, we use F equals QE, where Q is the charge and E is the field strength. Okay, the problem tells me that the field strength is 500 newtons per coulomb. F equals whatever Q is times 500 newtons per coulomb. This is a proton, and I gave you the charge on a proton earlier. It's the opposite the charge on an electron. So that would be positive 1.60 times 10 to the negative 19th coulombs. So I multiply 1.60 times 10 to the negative 19th coulombs times 500 newtons per coulomb, and I get that that charge experiences a force of 8 times 10 to the negative 17th newtons. It's a force, so it's newtons. So that's part one, what's the magnitude? The problem also says, what's the direction of the force? Okay, so I told you field lines point the way a positive charge would move. You need to beat that into your own head. Field lines point the way a positive charge would move. It's hard to remember because we like to talk about electrons, but the way field lines were set up by physicists is field lines point the way a positive charge would move. So these field lines are pointing up. This is a positive charge. The field lines tell me a positive charge moves up. So my direction there would be up. So my force expressed as a vector, because I put in direction, 8 times 10 to the negative 17 newtons up. Next, a uniform field of 2,000 newtons per coulomb points to the left. A particle with a charge of negative 6.5 microcoulombs is placed in the electric field. What is the magnitude and direction of the force on the particle? Why don't you try this one, come back and I'll show you the work for it. So pause the video, try this problem. Okay, so here's my work for finding the magnitude. F equals QE. The charge on the test charge is negative 6.5 times 10 to the negative 6 coulombs. The strength of the electric field is 200 newtons per coulomb. I multiplied those together and I got negative 0.013 newtons. Now that negative is interesting because it's already kind of answered the other question. The field lines point to the left, telling me which way a positive charge would move. Well, a positive charge and a negative charge in the same field want to move in opposite directions. And so, if the field lines point in the way a positive charge would move, the negative charge would do the opposite. So the negative charge would move off to the left. So that negative actually the negative charge would move off to the right. So that negative has kind of already answered the question. It tells me that it will go opposite the field line direction. But my final answer is the force is 0.013 newtons to the right. So field lines tell you the way a positive charge would move. Therefore, a negative charge will move opposite the field lines. And you've got to remember that. That can be confusing. The field lines point the way a positive moves, and so a negative will move opposite the field lines. And if you keep your negatives and positives around, they can kind of be a signal to you when you see a negative. Oh, this could be one where it's a negative charge, so it's going to move opposite the field lines. Final example. An electron in an electric field experiences a force of 1.60 times 10 to the negative 15th newtons downward. What is the magnitude and direction of the electric field in this region? So this goes back to when I told you the only way we can know where an electric field is and which way it points is to put a charge there and to see what happens to the charge. So we've put a charge somewhere, and we notice that it gets a force downward. Now we need to know what kind of field it had on it. To get the strength of the field, we'll just go back to the equation F equals Q times E. We know the force on it, 1.60 times 10 to the negative 15th newtons. That's our force. We know the strength of the... No, we don't know the strength of the electric field. That's what we're finding. We know the charge, since this is an electron, 1.60 times 10 to the negative 19th coulombs. It's negative because it's a electron. I can solve this equation real fast for E, just divide by Q. So I get F over Q equals the strength of the electric field, and that's 1.60 times 10 to the negative 15th newtons divided by 1.60 times 10 to the negative 19th newtons. And that will be my electric field strength. Well, this is an easy one. 1.60 divided by 1.60 is just 1. And then I subtract the exponents because it's division. Negative 15 minus negative 19 is negative 15 plus 19. So that's 1 times 10 to the 4th newtons, or 10,000 newtons per kilogram. Sorry, coulomb. Goodness, I'm making mistakes with my units here. And I noticed that I listed that charge wrong. That should be coulombs. So, charges in coulombs, forces in newtons, divide, I get newtons per coulomb. 1.0 times 10 to the 4th newtons per coulomb is the strength of my electric field. The question also asks for the direction. Field lines point the way a positive charge would move. So if this electron moves down, we know that a positive charge would move the other way, and so the field lines must point up because field lines point in the way a positive charge would move. So that's that strength, and the field lines are pointing up. So the electric field would look something like what I've drawn here in green, pointing up all around that electron. And that's it. This last example is especially important. If you did not understand it, please rewind. Also, hopefully my mistake there with the units didn't confuse you. Newtons per coulomb are the strength of an electric field.